Good afternoon, everybody. My name is Teresa, and I will guide you through this webinar today. This is actually our 30th webinar in the RUS Copernicus webinar series, so it is a little bit of an anniversary or a birthday for us, you could say. So this month, we will be looking at vegetation biophysical parameters monitoring for agriculture, and we will be using the Sentinel-2 data and the SNAP toolbox. This webinar is being recorded, and you will be able to repeat the exercise by yourself at your own time, so don't worry about that now. I will give more information about this later. Now first, I will say a few words about the outline of this session. We will start as usual with the RUS service introduction, then I will move on to a Sentinel-2, saying a few words about the satellite and its data. Then we will have a theoretical background part, which is a little bit longer this time, and then we will move on to the actual exercise, and finally we will close with a Q&A session. The whole session is going to take approximately 1.5 hours, and as I mentioned already, the webinar is being completely recorded, and soon it will be available on YouTube and rus-training.eu. So let's start with this RUS service introduction. So RUS stands for Research and User Support for Sentinel Core Products, and it is an initiative funded by the European Commission and managed by the European Space Agency. Its main objective is to promote the uptake of Copernicus Sentinel data and to support R&D activities. The service provides free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes which are pre-installed on virtual machines, and these allow you to handle and process the data derived from Sentinel satellites. So what do I mean by this? Well, with the large amount of data produced daily by the Sentinel satellites, the challenge is no longer the data availability, but rather the storage and processing capacity. To solve this issue, RUS offers virtual machines so that you have the appropriate computing environment to handle the data. And in addition to that, we also offer specialized remote sensing help desk that can help you with data selection, processing, or applications, and also dedicated training program, part of which is, for example, this webinar. We also have face-to-face events and now newly so-called remote face-to-face events, which enable you to get all the advantages of face-to-face events from the safety of your home due to the current situation. So let's move on to the RUS websites where you can find all the details. The first one contains all the information about the project, and it is also where you can register for the service and access your virtual machines. The second one, the one on the right, contains all the information about the training activities that we organize, such as this webinar. And finally, we also have our YouTube webpage that I already mentioned, so it's called the RUS Copernicus Training. And this is where you can find all of our recorded webinars and also this one in a few days. Okay, so now let's move on to the Sentinel-2 introduction. So for this exercise, as I've mentioned already, we will be using optical data provided by the Sentinel-2 satellite constellation. The Sentinels are a family of satellites that is built by the European Space Agency for the needs of the EU Copernicus program. Copernicus is to date the largest Earth observation program in the world, and all its satellite data are available under free and open policy to everyone anywhere in the world. Once the program is completed, it will be formed by 6 constellations of 2 satellites each, with the range of technologies from SAR to multispectral imaging and much more. The Sentinel-2 satellite constellation is formed by 2 identical satellites, Sentinel-2A and Sentinel-2B, who both carry identical multispectral sensor, acquiring data over all land areas in 13 spectral bands. The spatial resolution differs by band, with the visible and near-infrared bands acquired at 10-meter resolution, the red edge and shortwave infrared bands acquired at 20-meter resolution, and so-called atmospheric absorption bands acquired at 60-meter resolution. The data are radiometrically and geometrically corrected and cut into 100 by 100 kilometer tiles. They are also resampled to a common global grid for better handling, and you can also download level 2A data that are already atmospherically corrected and are available over Europe since the spring of 2017 and globally since the end of 2018. These level 2A data are the ones that we will be using for this webinar. So now let's move on to the theoretical background. First, let's have a look at agriculture monitoring. Agriculture provides humanity with food, fibers, fuel, and raw materials that are paramount for human livelihood. Today, this role must be satisfied within the context of environmental sustainability and climate change, combined with an unprecedented and still expanding human population size. On the graph, you can see visualized data from the World Bank and the Food and Agriculture Organization of the United Nations, showing a steady projected increase in the human population, and therefore also a decreasing arable land per capita. Currently, there is not many places on Earth where expansion of arable land is feasible, and almost always it comes with large environmental cost. At the same time, arable land is also subject to loss due to climate change, bad management, and other causes. There were incredible advances in crop productivity over the last century, but in order to be able to feed the ever-growing population in the future, more will be needed. In the light of this challenging context for agriculture, there is strong requirement for monitoring of crop growth and status in various locations with various temporal resolutions and for different purposes. Near real-time monitoring is also needed to react to extreme events according to the changing climatic conditions and thus to minimize their impact on the global food system, but also to optimize management practices in a sustainable way. So what do we mean when we say vegetation monitoring for agriculture? In agriculture, the information of interest consists of traits and features of agricultural systems and how these vary in space and time. Crop traits can be defined as characteristics that influence organisms' performance or fitness and differ from one plant, crop or area to another. The nature of these agronomic traits can be typological, such as, for example, crop type, physical, such as temperature, soil moisture or evapotranspiration, chemical, such as leaf chlorophyll or nitrogen content, biological, such as plant phenology, for example, structural, such as leaf area index or leaf inclination, and geometrical, such as, for example, plant density. So now, where does remote sensing come into this concept? In remote sensing, we measure the radiance, or in other words, the amount of light that arrives to the sensor from observed unit of area on observed object or surface. If we know the amount of incoming solar radiation and remove the effects of atmosphere, we can then derive the surface reflectance. For example, let's have a look at this typical reflectance profile of green vegetation on the right. In the visible part of the spectra, we have in general quite low reflectance. However, we can see that the reflectance peak is at the green wavelength due to chlorophyll absorption at the blue and red wavelengths. This is why we see vegetation or healthy vegetation as green. Then in the near-infrared part of the spectra, we have a very high reflectance caused by the plant self-structure, and in this part, the healthy plants will have higher reflectance than plants under stress. Finally, in the short wave infrared part of the spectra, we have water absorption peaks. However, simple radiance at pixel or even reflectance at a pixel is not directly translatable to plant biological variables. Number of additional information that comes with the radiation measurement is needed. These are, for example, the spectral information, so which band this information was acquired in, the directional information, the spatial information, such as resolution, and the revisit frequency. Now, plant characteristics vary from one individual, a plant, for example, a group, such as crop, or society, for example, an area, to another. But this spatial and temporal variation is of crucial importance in order to determine plant health and status. As for many other applications, remote sensing provides a perfect tool here. As in situ measurements can be difficult and expensive, remote sensing provides an ideal tool to map these variances over time and space. In general, we can define two categories of variables that can be derived from remote sensing. First, so-called canopy primary variables, which are variables directly involved in the process of radiative transfer, such as leaf area index or the fraction of absorbed photosynthetically active radiation. Or in other words, these directly influence the plant spectral response. The second group are canopy secondary variables, which are linked to radiative transfer indirectly. In general, they require additional information to be derived. For example, yield estimation requires primary canopy variables, such as leaf area index, but also information about the crop growth cycle, crop management, and climate and weather conditions. In this session, we will further talk only about the primary variables that can be derived from the reflectance directly. Unfortunately, it is not that easy linking the reflectance to biophysical variables, as it is so-called ill-post problem. This means that several combinations of variables can produce the same reflectance profile. There is a large number of methods developed today to tackle this problem, and we can divide them into two main groups. First one is so-called empirical methods, and the second one is radiative transfer model inversion. Empirical methods are generally easier and faster to implement, but they require a large number of in situ observations and are prone to overfitting to a single area, crop, or observation conditions. Radiative transfer model inversion, on the other hand, can be applied to a wider range of conditions, but makes certain assumptions regarding the canopy properties, such as canopy structure, which contribute to model uncertainty. In the table on the right, you can see various primary canopy variables that are derived from different remote sensing sensors. In this exercise, we will focus on the leaf area index, fraction of absorbed photosynthetically active radiation, chlorophyll content, water content, and green cover fraction. Now let's talk about each one in turn. First, let's start with the leaf area index. So what is leaf area index? It is the total one-sided area of all the leaves above given ground area divided by the ground area. For example, in a cornfield having leaf area index of 4, it means that above each square meter of the ground, there are 4 square meters of corn leaves. The amount of leaves in the canopy is a factor in determining the amount of light intercepted by the canopy, which in turn controls photosynthetic rates. Leaves contain pores, called stomata, through which carbon dioxide and water pass between the plant and the atmosphere. So the leaf area also sets limits on transpiration and photosynthesis. For different vegetation types, leaf area index can vary from less than 1 for deserts, for example, to over 6 or 8 for rainforests. There are a variety of methods for measuring leaf area index. The most straightforward is to simply define an area on the ground, clip off all the leaves, and measure their area. Dividing the total area of all the leaves by ground gives the leaf area index. This method, however, is time-consuming and has the added disadvantage of destroying the plants being studied. This method also produces what is called a true leaf area index. The second method is measuring the fraction of incoming light that passes through the canopy. This is done by making assumptions about how the leaves are distributed in the canopy and then measuring the size and number of gaps between the leaves. These two pieces of information can then be used to calculate the leaf area index. Canopy gaps can be measured using high-contrast photographs, looking up at the sky, through the canopy, or by recording the intensity of light transmitted down through the canopy. This method produces what is called effective leaf area index. When we use remote sensing, we estimate so-called apparent green area index. So we consider all the green units in the canopy, not just the leaves. Generally, the green area index or leaf area index has been estimated from remotely sensed data by developing relationships between the ground measured leaf area index and the spectral response at visible and near-infrared wavelengths, often using vegetation indices such as NDVI, for example. However, these often reach saturation once the leaf area index gets about 3 or 4, meaning that canopies with a leaf area index of 4 and 8 can have almost identical values. Leaf area index is also recognized as an essential climate variable by the Global Climate Observing System. Now let's move on to the next one, which is going to be the fraction of absorbed photosynthetically active radiation. Photosynthetically active radiation is actually restricted to just a portion of the sunlight spectrum from 400 to 700 nanometers, which is comparable to the range of light that a human eye can see. Absorption of light by chlorophyll takes place largely within a narrow bands that peak at 680 nanometers or 700 nanometers. Light absorbed outside the PAR region may be actually harmful to plants because it can rise the leaf temperatures and require heat dissipation through transpiration. When you look at the image, you can see the incident PAR, which is the amount of PAR incident at the top of the atmosphere. So that's right here. Usually we know it because it can be modeled using the Earth-Sun geometry and known solar radiation, and it varies seasonally with changes in Earth orbit and tilt, as well as with latitude, local topography, and through the day with changing sun angle, and variations in cloud cover and also atmospheric conditions. Then we have the intercepted PAR, which is the amount of PAR caught by various canopy layers as it travels down through the canopy layers to the ground. The absorbed PAR, or APAR, is the amount of PAR that is actually absorbed by the canopy leaves. So of course that the APAR has to be equal or smaller than the EPAR, or the intercepted PAR. The difference between EPAR or intercepted PAR and APAR or absorbed PAR depends on the canopy closure, coverage over background materials such as soil, for example, canopy composition, canopy density, and reflectance. If a canopy has complete, dense coverage and it consists of green leaves, then the EPAR might be a good approximate to the APAR since the healthy green leaves do not reflect much. For open canopies, or canopies that consist of both green and brown materials, EPAR and APAR may have a significant difference. Fractional APAR is simply the fraction of incident PAR reaching the canopy top that is being absorbed by the canopy. This value will be always between 0 and 1. Same as the leaf area index, FAPAR is also one of the essential climate variables, or ECVs, recognized by the Global Climate Observing System, or GCOS. Now the next variable we will talk about is the fraction of vegetation cover. It is a measure of the fraction of the landscape covered by vegetation. Canopy cover, like the leaf area index, is an important factor in determining the amount of light that is intercepted or absorbed by the canopy, and also of the photosynthetic rates of the canopy. Canopy cover also determines how much rainfall is intercepted by the vegetation before hitting the ground, which in turn affects the rates of evapotranspiration, erosion rates, and consequently it is important in hydrological studies. It can be measured using the same methodologies used for optical measurements of leaf area index. The canopy coverage is simply 1 minus the total gap fraction. So part of the interest in this canopy descriptor is that it avoids the needs to make assumptions about leaf spatial distributions required to calculate, for example, leaf area index from the gap fraction data. The remote sensing of canopy cover follows the same approach as for measurements of leaf area index, with the relationships developed between the canopy cover and spectral vegetation indices, and also has similar limitations. The image that you can see here shows the changing global daily fraction of vegetation cover derived from the Sudbury sensor. Now the next variable that we will talk about is the chlorophyll content. The chlorophyll content serves as a very good indicator of the stresses, including the nitrogen deficiencies in the plant, and it is strongly related to the leaf nitrogen content. This quality can be calculated both at the leaf level and at the canopy level by multiplication of the leaf level chlorophyll content and by the leaf area index. On the image you can see how different levels of chlorophyll affect canopy reflectance. Visible wavelength reflectance is decreasing with the increasing chlorophyll content here. And finally, the last variable that we will talk about is the canopy water content. So we know that water represents between 60 to 80% of the living plant mass. Since radiation is absorbed significantly by water in the near-infrared and middle-infrared part of the spectra, the spectral configuration of Sentinel-2 is particularly ideal for its derivation. The variable that is the best related to the remote sensing signal is defined as the mass of water per unit ground area, so gram per meter squared, for example. One of the difficulties in retrieving the variable is the possible confusion, for example, with soil moisture. On the picture, you can see the top of canopy reflectance modeled with a different water content, where the CW means leaf water thickness in centimeters, at fixed leaf area index of 4.5. All of the variables that we have just described can be derived using the Sentinel-2 SNAP toolbox biophysical variable retrieval algorithm that was developed by Mary Weiss and Fred Barrett from Indra. The algorithm consists of multiple artificial neural networks pre-trained on reflectances derived from specific radiative transfer models, and these are the SAIL and the PROSPECT models. So SAIL stands for scattering by arbitrarily inclined leaves, and PROSPECT stands for leaf optical properties spectra. And both of those are associated with strong assumptions, particularly regarding the canopy architecture. The algorithm is generic, so this means that it should apply to any type of vegetation with reasonable performances. However, some studies in the past have demonstrated poorer performance when radiative transfer models such as SAIL, which describe canopy as turbid medium, which you can see on the picture here, are applied over forest environments. Generally, in literature, you can find the performance of this algorithm is much better for canopies that are more representative of this turbid medium, which are, for example, various crops. In the references at the end of this presentation, you can find the links to the algorithm theoretical base document, where you can find all the details. And I would also advise you to watch a lecture given by Dr. Weiss as a part of the advanced training course on land remote sensing that happened last year, and it is available on YouTube. So now let's move on to the exercise. So first, few words about the study area and the field data. So our study area this time will be a large private farm northwest of Rome on the coast in the area of Macarese. It is a coastal area close to Rome, and it has large fields of approximately 15 to 100 hectares, and they also employ precision farming equipment. The field campaign that acquired the field data that we will be using during this exercise concentrated on the winter wheat crop, and it was acquired, and the data were acquired by the CNR and the University of Tustra and published as a part of the 2019 Advanced International Training Course in Land Remote Sensing in China. Their use was kindly permitted by Stefano Pignati from CNR. So let's now move on to the virtual machine. So now this is our RUS virtual machine. For those of you who are not familiar with it yet, let me first just increase the screen size to a full screen. And here you can see how the RUS virtual machine looks. It's a Ubuntu-based virtual machine with pre-installed tools such as Snap, for example, but also QGIS and a number of development tools such as Jupyter Notebook or RStudio. So to start the exercise, let's go to the training folder. And in the original folder, we have the original downloaded data. So I will not explain here how to download the data. The information is contained in the step-by-step guide that you will get if you request it on your virtual machine. And here we have 10 products that are of our interest. So we are using the Sentinel-2 level 2A data, which means that they are atmospherically corrected data already. And we are using data acquired from the 29th of January to the end of June 2018. Here, also in the name, just as a matter of interest, you have a specific name of the specific tile in the world grid to which this image belongs. And here the 32 stands for the UTM zone, and the TQM is a unique identifier of this tile. Okay, so now let's have a look at the images. Let's open the Snap tool. Okay, so this is just a check for updates. So all our updates are installed, and I can click Finish. And let's open the first product. So I click up here to the Open Product, and I go to the original folder. For me, it jumps there automatically, but you might need to navigate through the layers to the original folder. and then we open the first image. So I just double click it. It's a zipped file that you download from the Sentinel Open Access Hub. And let's have a look now at the structure of the file. So you can see that the file contains several folders. For us, the most important is this bands folder, which contains the spectral bands, but also information on the sun viewing angle and the quality flags related to the atmospheric correction. So first, let's have a look at natural color band composite. So let's go to Open RGB image window. And here we have some options of profiles that we can choose. These options at the moment are very limited, as we can only use bands that have the same resolution. And you remember I mentioned that not all the bands in Sentinel-2 have the same resolution. We have 10-meter bands, 20-meter bands, and 60-meter bands. So here, for example, the natural colors is using the 10-meter bands. Here the false color infrared is using well, in this case, also the 10-meter bands, and here the atmospheric penetration is using, I believe, the shortwave infrared bands. Okay, so let's open the natural color composite. So I click Open. And here's my, my data. So my area of interest is actually in this very corner. So let's zoom in to our area of interest, which is just north of Rome. So Rome is approximately here somewhere. You can also see the Fiumicino airport here. And this is our area of interest. So this is the Macarese farm or Macarese region. And let's open also another image in the false color composite view, just to see the effect of it. And let's go to Open RGB again, and then I will use the false color infrared. And again, I can zoom in to my area of interest. I can also use the window tile horizontally to have both next to one another, and they are linked, so they move in sync. There we go. Here you can see the Fiumicino airport, and here we have the area. Okay. So now let's proceed. You know that we have 10 images that we want to process. I did not load all of them, I only loaded one. And this is because processing 10 images one by one is relatively time consuming and not very effective, and in general we wouldn't want to do that for a time series. So what I will use here, we have several options what to use in Snap. We can use the built-in batch processing tool, or we can use the GPT tool, which is a command line utility of Snap. And this tool I prefer personally because it's faster. You can script, or you can be more flexible when using it. And it is also better in memory management than the graphical interface of Snap. So how do we use this? So first, what are the steps that we need to apply? So before we actually move to the biophysical parameter retrieval, we need to perform several preprocessing steps on the data. The first step is going to be subsetting to the area of interest, because the biophysical variables retrieval is actually very, very time demanding, and the bigger the area we have, the slower the processing will be. And the second one is, or the first one actually, would be resampling. The subset would follow it, and the resampling makes sure that all our bands in the product are resampled to the same identical resolution. This is due to avoiding problems with many operators, such as subset, for example, that cannot handle multi-resolution data. So to do this, we will first build a graph. So we go to Tools and Graph Builder. And a graph builder is a tool that allows you to define your processing steps, connect them into one processing chain, and then run them as a whole. So I could just here create my processing chain and then manually apply it also to every product that I could do as well. At the moment, the graph builder has two operators, which are read and write. So this operator reads my data and this operator writes the output. The nice thing about the graph builder, or using graph builder, is also that it does not save any intermediate products. So for example, if we do the resampling and we resample all our bands, including the masks, to 10-meter resolution, the resulting product is going to be gigantic, and it's going to take a long time to load, a long time to write, and it's just going to be very difficult to work with. However, we do not need all of these bands, or we might need all of the bands, but we don't need the entire area of the tile. So we then apply the subset, but only the result of the subset is going to be saved, which means that we don't need to save this gigantic amount of data. So to first create our graph, what we do first is we right-click and we add the resample operator. That is saved in a raster, geometric, and resample. Now you see that every time I add an operator, there is a tab appearing at the bottom where I can set the parameters. And I will connect my read operator to the resample operator. And then I will add another operator, which is the subset. So I'll go again to raster, geometric, and subset. Connect it, and finally I connect it to the write operator. So now this is my pre-processing graph. It's very simple. There is of course many more things that you could do, but for this application this is all we need. Now let's go down here to the parameters. So let me enlarge the window a little bit. So we have the read tab. Here we don't need to change anything at the moment. It automatically takes the open product as the source product. Then we have the write tab, which gives us the name of the output product and the directory where it's going to be saved. I will not change anything here at the moment either. And then I will go to the resample tab, which has a bit more options. So for resampling, we can choose 3 different options based on which we want to resample the product. We can choose to resample based on a reference band. So we can choose the band inside the product from which we want to take the resolution, or based on which we want to resample it. So as I mentioned, the bands 2, 3, 4, and 8 are, the 2, 3, 4, and 8A are 10 meter resolution bands. So I can, if I want to resample to 10 meter resolution, I can use the band 2 as my model band. Then we can have an option to resample by target width and height, which means that I will set in pixels how many pixels I want to divide my image into. Then the last option, which is maybe more sensible than the target width and height, is by pixel resolution. So for example, if none of the bands in my product is of the resolution that I would like to have, for example, here I have bands that have resolution 10, 20, and 60 meters, but I would actually want to have pixels of the size of 100 meters, then I can use the resample by pixel resolution and set my pixel size in meters here. And then finally down here we have the resampling algorithm that we want to use for upsampling. So some bands we will be upsampling. For example, now we use 10 meter resolution, so we are actually upsampling the bands that are now in 20 meter and 60 meter resolution. Then we have downsampling. That does not happen in the current processing that we have, and flag downsampling method. I will just leave the defaults here. And then finally we will go to subset. Now in subset we can subset either by source bands, so we can choose the bands that we want to include in our output. Here I will keep all of my bands, which means I will not actually click into this field. If you do select one or more bands, you need to select all of them, because otherwise the algorithm is only going to proceed with those bands that you selected. If I don't click anywhere, it will automatically take all the data. Then we have 2 options of the spatial subset. First one is based on pixel coordinates, and second one based on geographic coordinates. So the pixel coordinates are obviously the pixel coordinates within the tile. For Sentinel-2 you can theoretically use this, even for time series processing. Generally I would advise against it, however, because for most sensors you will not have the same pixel coordinates for multiple products. So in this case we will also be using the geographic coordinates, which are a bit more widely applicable, let's say. And here we have the world map, and I can zoom in so I see the position of my full tile. And now I actually want to paste in or copy paste in a well-known text format polygon How do I get this one? So what I can do, for example, is I can click here on this drawing polygon thing, and I can choose my area of interest, and I can draw my polygon. So this is, let's say this is my area of interest. And then if I right-click on it, and I go to well-known text from geometry, I can get this polygon, and then if I copy-paste it, and I click update, I can see that it shows now here as well. However, I actually have already a polygon defined, so I will delete this one. And then I will go to my training folder where there is this expression underscore vm.txt file, and I will open it in mousepad. And then I will copy the polygon in the well-known text format that I have here and copy-paste it here. And when I click update, you can see that the area has changed slightly, so it's much smaller now. You can zoom in. Okay, we don't see much on the background, but basically this is my study area now. Now the next step would be to save the graph. So let me save it. I want to save it in the processing folder of my training folder, so processing, and I will save it as step 1 underscore graph underscore. So I find from experience it's good to keep track on the names of your graphs, because otherwise you'll get lost. And now let's click save. So once we have done this, we can close the graph builder here. And what we could do now, we could, for example, use this graph that we have created and go to the batch processing, load it to batch processing, set all our parameters again, and process our data in the graphical interface. But as I mentioned, this is one version, but personally I prefer the GPT more. It is more flexible and also better at memory management. So let's now see how we can do it. So let's close the snap window. We'll also close the expressions underscore VM. And let's now go to my folder, to the processing folder where I saved the graph. So let me open the graph with mousepad. So automatically it will open because it's an XML in the internet browser, but I actually want to open in editable format. So I will open it in the mousepad. And this is how the graph looks when I open it. So it is an XML file. You can recognize an XML structure, and we have different parameters set here in the different nodes. So for each operator, we have a node. So for example, here we have node ID read. This is for our read operator, and it's closed here. Then we have the second operator, which is the resample operator. Then we have some parameters, and again the node is closed here. Then we have the subset operator. For each operator you can also see what the source product is. So here in the resample operator we can see that the source is the read operator. So whatever comes out of the read operator is then loaded into the resample operator. Now, in order to be able to use this in GPT, if we only wanted to run it once on this particular product, we could just go to the GPT, pass in this graph, or path to this graph, and run it. But if we want to actually run in batch, GPT unfortunately does not have a simple tool how to run in batch, and you need to use a little bit of bash scripting. So let's convert this graph into something that the bash script can understand and set parameters in loop and process multiple data sets. So first what we need to do, we need to delete this path, and we need to replace it with something that converts it into a parameter that we can then set. This will be $, an input. We can name the parameter whatever we want. So $, indicates that it's a parameter, and input is the name of the parameter. Now we need to do the same with the output. So again, I delete the path to the output. Be careful not to delete absolutely anything else, otherwise it will result in errors. Again, I'll delete it. I will put $, and output. Now, once I edited my file like this, I will save it. And now the file is ready to be processed in GPT. So when I say GPT, what it is that I actually mean. So GPT is a Snap utility or Snap command line utility. So if I go to the terminal and I type GPT-H, so help, I can see all the parameters or all the operators that I can use within GPT. Basically, all the operators that are available in the graphical interface are also available in GPT. Not all, but most. So if you then type, let's say I would want to see how the resample operator looks. So I type So I can also run single operators on my data here. And if I type with H at the end, I get the help. So here I have all what I need to set. So for example, if I want to do the resample operator or do resample my product, s source product equals, and this will be the path to the file that I want to resample. Then I have all the parameters set with the different calls here. Okay, and we can also see that this is the graph structure for the resample operator, the same way as we've seen it in the graph that we just created. So now what we want to do is we want to use this GPT to run all of the operators that we have set in our graph in a loop over many products or over 10 products that we have. So what we need to do, we need to use a little bit of bash scripting. And I've already prepared the code, so I will go here to code and step 1 script GPT. And if I open this in Mousepad again, there is few simple steps that I have here. So here in the line 1, we specify that the script should be run with the bash scripting language. Then we have the parameters or input parameters. So we have the output folder. This is where our outputs will be saved. Then on line 4, we have the output name start. Then we have the output name end. So those are just ways how to define the name of our output product. Here the name end, for example, is just the suffix of the format, or the output format. In this case, the output format will be beam-dim-map format, which is the default format used by Snap. And the start name is just something that we want to define to remember what the product is. So let's go now to the loop. So here we have the for loop. So I say that for each file in this path that ends with zip, so it is a zipped folder, I want to do first extract the product base name, so the name of the product. Then from this name I want to extract the date when the product was acquired, because it's contained in the name of the Sentinel-2 product. Then I want to create the output path and name of the product, which will be consisting of the output folder that I defined up here, then the name start that I defined up here, then the acquisition date, so this differentiates all the outputs that I will have, and the name end, which is here. And then finally I go to the actual processing. So for each of these products I want to go and do GPT, then I want to call my graph, so this is the graph that I saved in the processing path. And then I want to use the parameters that I have created within that file, which if you remember was $input, so my parameter was called input. And here I call that parameter by using -p and the name that I assigned. And I want that parameter or input to equal the path to the product that is derived here. Then I have the p output. So again, I had a parameter set in my XML file that was called output. So I put $output. I call it by using -p, and then I say equals output path name. So it will be equaling this, the result of this combined. So basically it will be the path and the name of the output product. And Then when I run this script, it will iterate over all of the files in my input folder and produce for each this output. Okay, so let's do that. So I close it now. I don't want to save changes, I just did that by accident. And let's go to the terminal. This time I will call the terminal by right-clicking into the folder where my script is saved, and I will say Open Terminal here, and the terminal window will be open. You can now see that actually the path to this folder is now here, and I can call my script this way. So the script is saved here, so I will just write sh, sorry, I have a caps lock on, so I'll just type sh, and then there we go. So this is the name of my script, and now I can click enter, and the script will start to run. So the processing of these two steps for 10 images takes a couple of minutes. It's relatively very quick. You can see that for the first product, it should be finished just by about now. Okay, so we are at 90%, and now it's done. And the second product is starting to be processed at this very moment. I will not keep the processing running, as I've already have the products processed or pre-processed prior to this webinar. So let me just close the processing. There we go. And I'll go back to Snap and have a look at my products. Okay, and I have previously created so-called session file for Snap, which loads all the products that we have now processed. So let's now load this session file. It's sort of an alternative, you could say, to a project in ArcGIS or in QGIS if you're familiar with them. So let's go to Sessions, Open Session, and I'll go to the training folder, and here I have the preprocessed.snap, which is the session file that will load all the preprocessed 10 products. So let's click Open. I do not wish to save any changes. And there we go. So now you can see that 10 products have been loaded. They are all the products that we have preprocessed with our bash script. And you can see that the name also corresponds. I have removed, when writing the bash script, I wanted to remove the Sentinel-2 A or B, so we can actually have them sorted based on the time of acquisition. And now let's have a look at the first one. So let's open RGB. Again, I will use the natural colors composition. So this is our study area in January 29th of January of 2018. Let's open the windows for all of them, and then let's have a look on how the reflectance or how the values develop. Okay, so here we have all the images open. Let me also do tile evenly here. There we go. One more thing. I'll just move the image number 10 at the end. Unfortunately, Snap is not very smart in this way. Okay, and now there we go. So this is January, then we have February, then we have 4 images in April, close together, and then 2 images in May and 2 images in June. And we can see how this area of the winter wheat changes. So here the vegetation is relatively new and sort of lighter green, then the color goes darker until the wheat actually ripens and becomes this golden color all the way here. And then we see also the difference with the bare soil here. So this is a different crop. I don't know which crop this would be. It would be probably corn or something like this. So we start with of course, empty field. And then here it was seeded, and we find that the vegetation or the crop is starting to grow. And now we get this very dark green green patch or green plot of vegetation here. Okay, so Next, we want to actually retrieve our biophysical parameters so we can monitor the plots or the fields, and we can see, for example, where the field is healthy, where it's not so healthy, what is the phenology, how it develops, and so on. Okay, so for this we will use this nav biophysical processor tool, and you can find it in the optical, land thematic processing, and biophysical processor. So actually there's not many parameters to set. We of course have the input and output, but in the processing parameters the only thing that we can set is whether we wish or not to export or to output these different variables. So you can also just choose to, for example, have the output only of leaf area index, or the FAPAR, or the fraction of vegetation cover, as you like. But we will choose all of them. Now again, I could run this either here for product by product. I could create a graph and run it in batch here in the graphical interface. Or I can now use actually the GPT tool again and run this, this tool within the GPT tool in batch for all my pre-processed products here. Now this, if I created a graph, it would only contain the read and write operators and the biophysical operator. So that does not seem really like we need to create a graph for this. So actually let's close this. And the only thing that we will need to do is to run the biophysical processor directly from, well, we will not run it directly from GPT, but we can run it directly without a graph. So first let's have a look about the structure of the processor and what are the inputs and input parameters. So I will type there we go, and -H. Okay, and here you can see what are all the parameters that I can set. They are basically the same as we have just seen in the graphical interface. So I have the source product, which is of course the input product. Then I have 5 Boolean values that say whether this particular or each particular variable should be output or not. And here I have the structure of the graph if I was using a graph. What we will now do is that we will again go back to the folder. I have prepared the bash processing script for this tool as well. It's saved in the code. So here we have the step 2 script GPT BioOp. So if I open it, you can see that it's very similar to the one that we have run for the preprocessing, but the only difference that here we have GPT and not a link to the graph or path to the graph, but directly the biophysical operator handle. And then as source, because that is how it is defined here, so you can see as source equals the path to each of our files. In this case we are taking the preprocessed files, so this is these that we have here visualized and saved in the preprocessed folder as a beam dimmap format. And then we have a -T, which specifies the output path. So here we have the output path name, the same as before. And also we have the format. So actually what we want to do here, we want to export our data as GeoTIFF. Just out of interest, we can then export them also to QGIS or other software, so we will export them as GeoTIFF. Okay, so let's close. And now again, I'll go to Open Terminal here. And I will type again SH. There we go, and I will run the script. The biophysical parameter extraction takes significantly longer time than the process that we have run previously. This will take for the 10 products approximately 45 minutes. So of course we will not wait for it to finish running. I have the data pre-processed, but when you're running it by yourself at home, count with the fact that it will be quite time demanding, even more depending on the machine, either virtual machine or your computer that you're running it on. Okay, so let me close this now and let's have a look at the results. those are saved in the processing folder in the BioOp folder. And you can see we have 10 products here, all saved as a GeoTIFF. And now let's have a look at them in Snap. So I have prepared again a session file as before. So let's open the new session file. And let's select the BioOp preprocessed or processed Snap. And there we are. So now we have our 10 processed products open. I have also opened the product, the first product that was just pre-processed, so it's only the one that has the resampling and the subset applied to it, and this is just so we can visualize also the natural color composite and compare it to our biophysical variables. Okay, so let's actually open those now. So let me first open the RGB image of the first acquisition, and we have seen this one already. Now the corresponding acquisition again here is the number 1, and let's go to bands, and now we can see that in bands we have always the biophysical variable band and the flags. So let's now open all of them except for the flags. So this is the leaf area index, this is the chlorophyll content, water content, fraction of absorbed photosynthetically active radiation, and the fraction of vegetation cover. Okay, so we have now all of them opened. Now I will just go to tile evenly. Let's center on all of the images. Okay, so now they are, you can see a bit, but they are black and white, so we cannot really differentiate all that much, except for the fact that if the value is high, then, for example, for leaf area index, of course, the bright values will be the higher leaf area index, and the darker values will be the lower leaf area index. Let's have a look at the color manipulation tab. So if I click into this window, into the leaf area index, I can now see that the minimum value, okay, is here in minus. So this is some sort of error that probably comes from the borders of the image and so on. And then here we have the maximum, which is 6.6. Now let's visualize the data a little bit better, and let's load color palettes that I have prepared up front. And I can load it by going here to this icon, import color palette from text file. Right click, and in the aux data folder, so in the training folder there's a folder called aux data, and in it you have the color palettes for each of these variables. So let's choose the leaf area index in this case, and I always want to keep the setting as it is in the color palette. So I want to say that I don't want to stretch the values, I just want to keep it as it is. Which means that in my color palette I have 0 set to this yellow color, and then 6 as a maximum set into this dark green. So now this is my visualization. Now I can do this for each one of them, so let me do that. So for FAPAR, and there we go. So here I have visualized the first product. Of course, over time and in our 10 images, these values will change for the different fields. But this is just a first look how it would look. Don't focus so much on the color palettes. Those are not prescribed in any way. I just chose color palettes that would be a little bit different from one another. But of course, it's good to know, for example, what the minimum and maximum values can be. So for leaf area index, in the algorithm, the valid values are specified as values between 0 and 8. Then for FAPAR, of course, it's a fraction, so the valid values are between 0 and 1. The same also for FCover, which is between 0 and 1. And then here the chlorophyll content, the valid values are between 0 and 600 grams per centimeter squared. And for the water content, the valid values are between 0 and 0.5, if I'm not mistaken, and the unit is grams per meter squared. So there's a difference between the unit of chlorophyll and water content. Now this visualization is nice, but of course it doesn't tell us a whole lot about the time series. So how can we actually see how the values develop throughout the observed period? To do this, we will use the time series tool available in Snap. So it's right here. And let's open it. So I just click on it. Okay, it opens here for me, but I actually want to take it and put it here to the side and make it also a little bit bigger. Okay, there we go. Now I have nothing, of course, in the time series, but I can choose my products. So I will go here to settings. And here I have to choose all the products that belong to my time series and that I want to visualize. So I can click on Add All Opened, which will add all the products that I have opened in my Product Explorer. Just don't forget that the last product that I have opened does not actually belong to this time series because it's just the reflectance data. So I will close this one. So this is my my time series now. I can see that it's also ordered correctly. If it's not, I can reorder it using these arrows here. And I have my acquisition date shown here as well. And I click Apply. Okay, and now I can close the window. Okay, so now I have other options. For example, here, basically the line that will appear will follow my cursor. I click into the image. Now there I have a line. Although here at the very moment I don't actually know which band this line corresponds to. So it can correspond to lie because I clicked on it, but that is not very certain. I actually don't know what it corresponds to. So we have to go here to the selection or settings, and we can choose which band we want the graph to show. So let's go to leaf area index. Okay, and let's click here. And you see that as I move my mouse, so for example, this is the winter wheat field, you can see how it changes. So basically as of May, there is a very low leaf area index, which corresponds to the, so we have to understand that the leaf area index here is actually the green area index. So even though the winter wheat is not harvested probably at this point yet, it's not green anymore, which means that it does not show in our green area index values. But here in January, you can see that the leaf area index or green area index values are very high or higher. They are depending on where we are. So here, for example, they're close to 5. If I go to this area here, also it seems very high. And if I go here, I can see that the graph now is reversed. So I have a bare field or bare soil until beginning of or mid-April. And then I start to have a growing crop on this area. I can also have a look at the other variables. So if I go back to my available bands, I deselect my leaf area index. And for example, let's have a look at FAPAR. And we can see that here the values, okay, you have to see that 0 actually is here on the graph. So we have the values again very different, but they follow more or less a similar trajectory. We can also have a look at the chlorophyll concentration, for example. Again, for the winter wheat, you can see a similar curve of the graph, and also for the other field where we don't actually know what is being grown. So this is one way how you can see the temporal development of the values for single fields. Unfortunately, the time series tool in Snap is not ideal. It is primarily designed for looking at SAR data or radar data. Ideally, we could set, for example, pins, for example, here and here, and we could then see the specific line for each of these points, and we could also see their difference. Unfortunately, at the moment, this is not possible in Snap or in this version of Snap for optical data. So we have to find a different way how to do this. Now what I have done in order to be able to show you the comparison of the values for a specific point, I took screenshots for a specific pixel and I have them in the presentation, so let's just open it quickly. There we go. So here, this is a specific point within the field of the winter wheat. You have it indicated on the map, also with a screenshot of the field and for the variable in question. So, for example, here in the beginning, we have the leaf area index and how it develops between so end of January to end of June for this pixel that we have indicated here. Then we have the same for the chlorophyll concentration or chlorophyll content, for the water content, for the FAPAR also, and for the F cover. Okay, so this is just to show you the time series. Let's go back to the virtual machine. So, of course, taking screenshots, it's not ideal, but there's alternatives that we can use and that are even better, I would say. So what we can do, we cannot export the data here, but there's a very useful tool in Snap that allows us to export the data for specific points. I will show you just in a minute, but now we will actually move on to the validation part of the exercise. So I have mentioned already that we have in situ data that have been acquired by the CNR and the University of Tuscia over this area. We have 4 dates on which this data has been acquired, which is 29th of January, 13th of February, 6th of April, and 19th of April. You can see that all of these actually correspond to images that I have here, so the first 3. And then we have the 19th of April, which also corresponds to an image, but unfortunately that image was cloudy, so it was not selected for this exercise. But we will match this, the measurements done on the 19th with the image from the 21st, which is 2-day difference, and we can also then see what affects this delay or this difference in the time of acquisition of the in situ data and the satellite data has on our accuracy. Okay, so if we want to, let's first close the time series plot. And if we now want to run the validation, or we want to do a validation, let's open another session file just to have it a little bit more simple. So I'll go to session, open session, and I will open the validation session. Now this session only contains 4 images. Those are the ones that are a match with our field data. And the first thing that we need to do is we actually need to load the field data into our images. So how do we do this? I select the first image, and then I click on Vector, Import, and Vector from CSV. And the data are saved in the AUX data folder. So I go to my training folder and field data, and here I have them. So you can see that I always have a text file that contains the data. Let's have a look at the text file in reality. So let's first go. And let's open, for example, the 6th of April. So this is the structure of the file. You can see that I have, of course, the headers here, latitude, longitude, acquisition date, field number, quadrat, and so on. And I have 13 points here for the 4th of April. And then here I, of course, have all the measurements, like the leaf area index, FAPAR, F cover, chlorophyll mean, and chlorophyll mean, yes, and leaf content, chlorophyll leaf content mean. I will do only the comparison for the leaf area index and the FAPAR and the F cover. Okay, so let's close this window and let's go back to Snap. And now here for the 29th of January, I have to select the 29th of January observation. So let's just click on it. Click Open. Now you have to choose which coordinate reference system your data is in. So we know that it's latitude, longitude based on VGS 84. So let's just click OK. And now it's asking me how the software should interpret the data. So I want actually to leave the imported data unchanged as points. You can also import point data as vertices of single line, for example, or as a track point. But we will not get into this now. We will just keep the data unchanged as points. Okay, and let's open a visualization so we can see how the data shows up. For example, if I open the leaf area index, here we go. Again, it's in black and white. And in the vector folder here, I can see my data. So I can double click on it and you can see that all the information is now imported here. Let's close it. Okay, so now what I can do is I can go to correlative plot here, click on it, and now I can set my parameters. So first I will actually click into the view. This will minimize the window again, but just to make sure that it knows which product I want it to be applied to. Then I will go to the point data source, and automatically this loaded CSV file or TXT file should be here. So I select it, and then since the software reads it, I will choose which field I want to use in the correlative plot. So I will use here the leaf area index, of course, because that's the one that I have open here, the leaf area index as well. And I can also, for example, show the regression line. So I can see, okay, here I have quite a few points only. So for the 29th, I have 9 points. But you can see that the coefficient of determination actually is very high here. The regression line is not exactly one-to-one, but the results look very good indeed for leaf area index. Now let's have a look for a different one. So for example, if I go to the FA-PAR, and I will go back to my correlative plot, and you can see actually that now it looks very different, and this is because I'm still using the points of LAI or leaf area index, but now my image that it's looking at is actually the FA-PAR. So let me change also here to FA-PAR. And there we go. So it is a little bit worse than for the leaf area index, but we can see also that the data are agreeing quite well. So we could do this for every single output that we have here, of course. Let's say also for fcover. If I quickly do the same. And again. Okay. So we can, for example, also select here the box size. So if we don't want to consider the exact point pixel value, but we want to rather have a look at, let's say, 3 by 3 pixel 30 meter plot, we can, for example, choose the box size of our original data to be compared, or of our image to be compared with the point data that we are importing. Or we can, for example, show a tolerance range depending on the percent and so on that we select. Okay, so this is one way how to compare our data with optical data, but you can see that it has some limitations. We can only have a look at one single band and one single time at a time. So how do we do actually that we can compare all our in situ data as a whole with all our images? So Snap has this very, very useful tool which is called extract pixel values, and let me show you how it works. So let me close the correlative plot, and now so for this extract pixel values we of course need pixel locations. So what I have done is that I have created this TXT file. It looks exactly the same as the previous one, but this time it contains it contains the latitude, longitude for all the observations on all the days, and also, of course, all the values. So now I have all my institute observations in one table. So now, let me close here, and let me go to raster, export, and extract pixel values. And here in the extract pixel values, you have a number of options. So this tool is actually really, really useful. And you can, for example, add all your loaded files. So let's say I want to say add all products. There we go. Now I have my all 4 products. And now what I can do is actually extract time from the product name. So of course this means that you have to have the date of acquisition, date and time of acquisition in your product name. But we do have this because Sentinel-2 products have it by default and we kept it. So we can say extract time from product file name. Now you have to choose here which format your date time pattern in the file name is. So here we have 4 digits as a year here, then we have a month, and then we have day, 2 for each consecutively. Now to say how do we extract, so basically here we have to edit this a bit, because if it was the original Sentinel name, this would correspond to the original Sentinel-2 product name. But for us, actually, we have changed it. So now it only contains one date, which we can consider, for example, the start date. So we have basically any character in front of it that would correspond to all of these characters. Then we have the start date or date. And then again, any character afterwards. So this will basically extract this value here. And the next step, what we want to do is we want to choose where do we want to save our extracted pixels. So we will save them in the processing folder again, and we can choose the prefix of the file that we want to give. At the moment, I will just leave it by default. Now, once we do this, we can go to the parameters tab, and here we need to choose which points or for which points we want to extract the pixels. So to do this, we will now use this file that I have just showed you. So let's click on it and let's say add measurements from CSV file. And then those are saved in the aux data, field data, and it's this one. And now here I of course have the ID, the latitude, the longitude, and the time that the measurement was made. Well, not time, the date that the measurement was made. Unfortunately, I do not have the time, but it's not, at this point, it's not really important. If you want to be very, very precise, of course, it would be ideal to have measurements from exactly the same time when the satellite passes, and then you can compare also here. Now, I have these points, and if I just leave it like this, the pixels will be extracted from every single image. This is not very useful to me because I only want the data to be extracted from the first image from 29th of January for the column or for the part where the date acquisition of the in situ data is also 29th of January. So I actually want to use time difference constraint, so I select it. And here I can choose how many days, hours, or minutes my difference should be, maximum difference. So here you know that for 3 of the images I have data acquired, in situ data acquired on the same exact day, and for 1 it's 2 days earlier. So actually I will set my constraint to 3 days because I know that it will not overlap, it will not create any confusion, so 3 days. And now I want to export only the bands, so I will select the tie point grids and the masks here. Window size I'll keep as 1, so 1 pixel per 1 value. So I do not need to choose any pixel value aggregation method. If I, for example, wanted to choose a box of 3 by 3 pixels, I could select 3 here, and then it would offer me, let me show you. So if I put 3, I can either choose no aggregation or I can choose mean, minimum, maximum, median statistics of that area. But I will choose none, so 1 pixel. Then you can also use an expression to apply to your values. Again, we will not do this. We can also export subscenes, and here we can export the output coordinates to Google Earth KMZ. That's quite interesting. But here, what is important, we can also match with original input. So you remember the table here also had the values of the in situ measurements, but they're not here. So we want to include the original input also in the output. Okay, perfect. So now we have set all of these and click extract. And now our pixels are extracted. And let's have a look at them. So let's go to my folder. And now in my processing folder, there is these two TXT files. So I have the product map, which just contains the products from which I have exported my pixels. And then I have the actual exported pixel values. So here they are. So let me show you. I'll close this. So if I open the file in the LibreOffice, for example, this is what I get. So here I know that it's very small and hard to see, but basically what you can see is the original table. And then I start with the extraction. So I have latitude, longitude of the extraction pixel or extracted pixel. Then I have the pixel X and Y coordinates. I have the date as extracted from the name of the product. Time, of course, is 0 here because I didn't extract it. And then I have the pixel value of each product at that point. And this gives us a lot of opportunities then how to compare the data further. So I will not go into how to work in LibreOffice, or you can download it from the virtual machine and export it to Excel, for example. And then if you create graphs, this is, for example, what you can then have as a result. So this is graphs for the leaf area index, the FAPAR and FCover. And you can see that I have the one-to-one line. I have all the dates indicated here with different colors. And of course, I have this fitted regression line for the whole data set here. And you can see actually that for leaf area index, the value is quite good, or the coefficient of determination value is quite good. Then I have the FAPAR, which is not so good in this case. And FCover also gives me a very good coefficient of determination, although it's not, you can see that there is a bit of a bias that is not, it's not directly one-to-one, let's say, relationship. Okay, so this is how you can validate your data, how you can test whether the algorithm performs well. In this case, I think for the fact that it's a generic algorithm that should give reasonable results for all the different vegetation, and it's not specifically designed for the winter wheat that we are using it for here, it actually gives quite nice results. We also didn't really clean the data any further and so on, so we might have introduced also some additional issues here. Okay, and finally, what you can do when you are creating the time series, you can use exactly the same tool that we have used here, and you can just choose, for example, a single point. So let's say that I start again and I remove all my inputs here. And now what I want to do, I want to create, or I want to extract a time series, the same way I used here the time series tool, of all my processed images over time. So I haven't actually, in preparation for this webinar, only processed those 10 images, but I processed about, I think, 61 images in total since 29th of January 2018 until end of March 2020. And I can load them by going here to the plus and add directories. And now I simply, in the BioOp, can add all of my directories. And now I have to choose what is my pattern. So my pattern for the recognition of the files is going to be any file that ends with .tiff, so any TIFF file in that in these folders. Again, I know that the data are called the same way as I had before, so I actually want to extract the date time pattern. It will be the same as here. Here, let's put, just to differentiate it from the previous extraction. Then we here go to parameters, and here I can load again measurements from CSV file. So from these points I want to extract my values. This time, however, I don't want to use the time constraint because these data do not have any time. I want to extract for these points the entire time series, so all the data from all the images that I have. I want to use the bands. I want to use, for example, 3 by 3 window size. I want to use pixel value aggregation method as mean. I do not want to use any expression, and I want to include also my original input. Okay, and if I do extract, now there we go. So it has been extracted, and we can now process it similar way, or open it in the LibreOffice and visualize the time series in a similar way as we have done before for the validation. So actually in the virtual machine, this is all that I wanted to show you today. I hope it was useful. And let me move now into the presentation. So here it's just the validation graphs that I have already showed you. So on this slide you can see the time series for which we have just exported the data. Here is the field that we are considering, and this is the point. The field is a winter wheat field, so we can see that in the beginning of the year it has high leaf area index value, so the time series is of leaf area index here in the green, FAPAR here in the blue, and in yellow it's the F cover, or vegetation, fraction vegetation cover. You can also see that the time series is not quite smooth, so here we have some data missing. Here obviously something is happening here. So this might be due to the fact that when I have created or processed the data, I didn't filter out well data that, for example, are contaminated with cirrus clouds, or for which, for some reason, the extraction of the biophysical variables did not go very well. So, for example, here these values for sure would be something where we would need to check the data, because this would not make naturally much sense. So the last slide that I have here for you is actually a GIF, and this is my time series over the 2.5 years looking at leaf area index. So there is this very interesting tool also associated with Snap, which is called P-Convert. It is run in the same way as GPT. If you want to have a look at it, you can use this tool to export specific bands of your product, for example, like lye in this case, into an image like JPEG or anything like that, using a specific color palette that you define. It's very useful actually, because then you can easily create GIFs like this using some online tools for GIF creation, or Python if you're familiar with it, and so on. Okay, so this is all for the exercise. I hope you have enjoyed it. I hope you have learned something new today. And here is the references and links for all the important documents. For example, here in the bottom, this lecture by Dr. Weiss on leaf area index, F-cover, FAPAR, and chlorophyll retrieval concepts and methods that was given at the 9th advanced training course on land remote sensing in the University of Louvain is very, very interesting, and has all the concepts that you really need to start to understand this problematics. The other papers are also very useful. For example, here you have the link to the algorithm theoretical base document, where you can learn about exactly how the algorithm performs the extraction and so on. So I hope you have enjoyed this training and that you have learned something new today. And here is the code that you need to insert if you wish to request the tutorial material, training material on your virtual machine, on your RUS virtual machine. And you can, if you don't have a RUS virtual machine, you can request it at rus-copernicus.eu. And here on the rus-training.eu, you can learn about all our new trainings and webinars and any events that we do. You can of course also follow us on Twitter, LinkedIn, Facebook, or rewatch any of our webinars on YouTube. Also, please don't forget to fill in our feedback form. It should appear to you just at the very moment that we close the webinar, or that you leave for the webinar. Otherwise, you will receive it by email. It would be really helpful for us if you filled it in, because it helps us to improve our webinars and see what your opinions and what your ideas are about them. So thank you very much. I don't see any more questions, so have a very nice day, and see you at some of our future webinars. Bye-bye.